In this tutorial, we'll be solving the circuit shown on the screen, which is a difference amplifier. And the purpose of the difference amplifier is to attenuate the signals that are common in the two inputs and to amplify the signals that are different. And in that sense, we can think of our source, our test source that we would put onto the circuit as consisting of two separate inputs. One is the common mode input, and then the other is the difference input. And if we can find the difference gain and we can find the common mode gain, then we know something about the quality of the difference amplifier, because an ideal difference amplifier would have a common mode gain of 0. So let's solve this problem, but let's first solve it by superposition. And then later we will step through and solve it in other ways. So to solve it by superposition, what we would like to do is we would like to ground one of the inputs and then put a test source, which I'm going to call Vn1, onto the other input. So when Vn2 is equal to 0, what is the output in terms of Vn1? And when we ground the Vn2 terminal, because there's no current flowing into the op-amp itself, the potential at all of the nodes of that resistor network will be ground potential. And so the positive pin of the op-amp is at ground potential. And so if you recognize that to be the non-inverting, the inverting configuration of the op-amp, then V out is just minus R2 over R1 times Vn1. And if you don't recognize that, then use the virtual short to recognize that the potential at the negative pin is also 0 volts, and then solve the problem like we have been. When we now ground Vn1 and we put our test source at Vn2, then the potential at the positive pin is set by the voltage divider circuit. So it is R4 over R3 plus R4. And this circuit with R1, the input at R1 at ground potential is in fact the non-inverting configuration. And so when Vn1 is equal to 0, V out becomes 1 plus R2 over R1, that's the non-inverting configuration gain, times the potential at the positive pin. So this was Vn2, so we can write that down. R4 over R3 plus R4 times Vn2. And now, by superposition, we can combine these two to determine what the total gain is going to be for the circuit. So V out will equal 1 plus R2 over R1 times R4 over R3 plus R4 times Vn2 minus R2 over R1 times Vn1. Now, this circuit becomes a difference amplifier when the constant in front of Vn2 is equal to the constant in front of Vn1. So we can write it in this form. AD times Vn2 minus AD times Vn1, which is just the difference gain times the difference between the two inputs. And for this to be true, we need to set those constants equal to each other and see what the ratio of the resistors are that give us that type of performance for this circuit. So we write 1 plus R2 over R1 times R4 over R3 plus R4 is equal to R2 over R1. Because when that is true, we can rewrite the equation like we've just shown. And so in this case, what we can do is move the 1 plus R2 over R1 to the right-hand side. Which then lets us write it in this form. 2. And then we can further rewrite this as R1 R4 plus R2 R4 equals R2 R3 plus R2 R4. And the R2 R4 terms cancel each other out. And then we can write this as R1 over R2 is equal to R3 over R4. So when this is true, we have a difference amplifier. And the difference gain will be R2 over R1. Right? Now, if we're interested in finding the common mode gain, that is when we provide the same signal to both inputs. We can use the expression that we already derived up here that I'm going to box in, and just set V in 1 and V in 2 equal to V common mode. And so V out is equal to 1 plus R2 over R1 times R4 over R3 plus R4 times V common mode minus R2 over R1 times V common mode. Right? And so the common mode gain is going to be, we can just write it like this. And so that allows us to solve for the common mode gain. So we said the difference gain was R2 over R1 when this is true. And then the common mode gain is this expression right here. Okay? And when that expression up above is true, the common mode gain will, of course, be 0. And so what it allows us to do now is to look at the circuit in terms of its ideal difference gain, and then its common mode gain when 1 or 2 of the resistors are slightly off, and see how sensitive the circuit is to small errors in the resistor values. And remember, the common mode rejection ratio will just be 20 times the log base 10 of the difference gain divided by the common mode gain. And so the common mode rejection ratio is going to be 20 dB when the difference gain is at least an order of magnitude larger than the common mode gain.